Okay, in this chapter we will study ideals. Ideals are a very fundamental concept in algebra in general, and it is very important. We have learned about subgroups. Given a group, then we have a subset of that group, which is called subgroup if it satisfies some axioms. And we learned about some kind of subgroups called normal subgroups. Later we learned about rings, and then we defined subrings. Okay, and we gave a theorem where we show that a given subset of a ring is a subring if it satisfies two conditions. We will use these two conditions today. Now we will define ideals inside rings. They are subset. Actually, they are subrings with one more condition in there. As we see in the definition here, an ideal I of a ring is a subring where the following is satisfied. So here you go. We start with the definition of ideal. What we mean by an ideal I is a subring of a ring R, provided that if we have any element in the ring R and any element from the subring I, and then we do the multiplication, the result of the multiplication will be absorbed in I. Whether this multiplication is R times A, the element of the ring is to the left and the element from the ideal is to the right, or A times R. In both cases, the result stays in I. If this happens for a subring, then we will call this subring an ideal. Okay? So I would like to rewrite this word here again, because this is very seen very much in algebra, a very important definition. And before we keep going, I would like to demonstrate, give a graph, so that which might help you to have some sense or imagination of the definition of an ideal. So if we have a ring R, and say we have the subset or the subring for now, the subring I, so I will claim that I represent this by I. Okay. Now what is this says? It says if we have an element here in A, so in I we are choosing any element inside the ideal I, and take any element inside the ring R, then do multiplication. So I will assume their multiplication. I will represent it this way, but I have now to represent the multiplication, so I will use this arrows to denote their multiplication. So the multiplication must live inside A, side I, sorry. So choose any element from the ideal, from this subring, which we call an ideal, and any other element from the ring. Multiply, the result will be inside the ideal I. So we will say I absorbs. So we may say I absorbs the elements of R. Absorbs here, like I will put it between quotation marks, which means multiplying an element from I with any element from R, the result shall stay, will be absorbed inside R. And This will also implies that if A is an element in I and R, I said any element, small r, any element in the ring, it could be from I also. So both elements A and R could be from inside I. We still see that multiplication shall stay inside I. Okay, now this is the definition of ideal, and let's see examples. The zero ideal, simply if we have a ring R, then we can choose the trivial ideal, which is the zero of R, and this is true. So I shall put it inside. It is a set inside the set notation. So this is true because if R is any element in the ring, then simply R times 0 equals 0 times R, which gives the 0 of R, and that belongs to I. So if we choose any element from the ideal I, right? But we have only here one element, which is the 0. So again, what's happening here is for any element A belongs to I. Okay? And any element R belongs to the ring. Okay. Now the subring, we know that Z is a subring of Q. Remember that Z is a subring of Q, where addition and multiplication are the regular ones. But Z is not an ideal of Q. How to show a given subring is not an ideal? Simply look for an element in the ring, which is a Q here, and some element in the subring, which is Z, multiply them, and the result will not be in the subring. For example, if we choose R to be 1/2, this belongs to the ring R, which is Q here, and choose any element in Z, not 2, I will choose like 3 belongs to Z. Okay, but this is for A, as in the above definition. R times A equals 3/2. It does not belong to Z. That's why Z is not an ideal inside Q. Or inside the real numbers, we can replace same thing, same proof will work if we choose the ring R to be real numbers, or if we choose it to be the complex number. So we have an example for an ideal. Okay, more examples of ideals. In here, the ring Z of X of all polynomials with integer coefficients. Okay, so this notation here, this notation denotes all polynomials. You know polynomials, they are summation of powers of X. The powers are integer powers, and the coefficients here are coming from Z. That's why we have Z in here. If we, for instance, write R, this is the real number, and this is X, we will denote, this denotes all polynomials, but coefficients are from the real numbers. Okay, we can define same thing, but using the coefficients to be from the rational numbers. All polynomials where coefficients are coming from rational numbers. Each one of these is a ring. Actually, this is a topic of chapter 4, and we did not cover it. All what we needed from there to accomplish this course is to know that each one of these sets is a ring. Okay, so we will take an ideal of this ring. We go back to this ring here, the ring of polynomials with integer coefficient. So all polynomials with integer coefficients. Now the ideal I, take it to be the set of polynomials whose constant term is even. You know that polynomial have a constant term. So we will take the set of all polynomials with integer coefficients whose constant term is even. And remember that 0 is even number. So, for instance, x cubed plus x plus 6 is in I because the constant term here is 6, which is even. We could make like 7 as a coefficient here, or 5 here. Still, we don't care for any term in the polynomial except the constant term. If it is even, then it is in I. But this polynomial here does not belong to I, because the coefficient, the constant term here is odd. Okay? Now, we claim that I is an ideal in z of x. Now, how to prove an ideal so far? First, prove the given set is a subring. Okay? And how to prove a given set is a subring? Remember that I will write the outlines for proving this. So to prove I is an ideal, we need to show first, okay, it is a subring. So we will show that f of x minus g of x belongs to I, okay, for all elements which are polynomials now inside I. So this is the first axiom of a subring, right? The second axiom of a subring is that their multiplication also belongs to I for all, again, f of x, g of x belongs to I. Okay? And now the third thing to prove, which is the absorption property, which means that if we multiply h of x times f of x, or f of x times h of x, then each one of these must belong to I, where f of x is any element in I, and h of x is any element in the ring z of x. So the coefficients are integers. So prove these three things, then we will be done. Okay? In a little while, we will notice that actually, we will see a theorem. This is guaranteed. We will show this is guaranteed, because if we prove 3, then we don't need to prove 2 anymore. 2 says if you multiply 2 elements from I, then you stay in I. 3 says if you multiply an element from I and any other element in the ring, the result shall stay in I. But any other element in the ring means it might be chosen from I itself. So part 3 in here covers the case where both elements from I. We will see that within a theorem. Okay, so what we achieved in this example here, that this ideal, which consists of all polynomials of integer coefficients whose constant term is even, is an ideal. So this subring is an ideal. Okay, another example of ideals is the following. If we choose I to be all matrices, 2 by 2 matrices of this form. Now we have 0 at this entry, 0 at this entry. A in here can be any number, and B in here can be any number, real numbers. Then this is a subring, and we have encountered this before. Okay. Okay, it is a subring, yes, or you prove it. And it is easy to see that I absorbs products from the left. So above there I said I absorbs the elements. So this is a better way to say it. I absorbs the products on the left, which means if we choose any element from, this is any element from the ring, which is M of R, and this is an element from I. Do the multiplication, simply we will find the resulting matrix to be in I. Okay? But in here, what is interesting about this example, it says that it absorbs the product on the left. Okay? So that means in the definition we have R times E. So the element from the ring is to the left, stays in I. But in here down, it is not true that if we put the element of the ring to the right, then we will find that the result is not absorbed in I. How do we know this? But I is not an ideal because it is not. It may not absorb products from the right. Okay, so this is an element from I, and this is an element from M R. But when we multiply, we find it does not belong to I. Okay, so what happened here? The elements of I, or I absorbs products from the left, but from the right, not from the right. And we may say in such a case, I is a left ideal. In this case, we say I is a left ideal. Okay. We are more interested here actually on ideals, both left and right. So the original definition of ideal implies that the left absorption of product and the right absorption of products. Okay, now so far if you are given a subset and you are asked to prove it is an ideal, then you need to prove first it is a subring, then you prove the absorption property. But actually all of these are collected in one theorem, in two axioms as following. So we will adopt the axioms in this theorem to show that a given subset is an ideal. But first here it says a non-empty subset. Okay, a non-empty subset I of a ring is an ideal if and only if it satisfies the following. For every AB belongs to I, their subtraction is in I. So that axiom is to guarantee it is a subgroup, right? Okay. And then this is the absorption property of I that we know. Okay. So to prove it, let's prove this direction, which is direct. I can see. I want to say. So if we assume if I is an ideal, then for sure, by the definition, then I and 1 and 2 hold directly, right? Because if it is an ideal, then it is a subring. So it is a subring, it satisfies these two conditions. Okay. Now to prove the opposite, we will show that if these two axioms are satisfied, then we have an ideal. Okay, but go back to the definition of the ideal. It says it is a subring and satisfies the absorption property. So we need to prove these two things. It is a subring and it satisfies the absorption property. But we have in hand the absorption property given in 2. So it is already given. So by 2, we only need to prove that I is a subring. Okay, so we want to prove I is a subring, but let's go back and remember what are the axioms needed to prove it is a subring. We have seen in a theorem that a non-empty, if S is non-empty and 1 A minus B belongs to S and 2 A times B belongs to S, and this is for all elements A and B in S, then S is a subring. Remember, the definition of subring needed for axioms. But later in a theorem, which is this theorem, we showed that these 4 axioms can be reduced to 2 axioms if we know that S is non-empty. So the set in here is non-empty, so we only need to show these 2 axioms here, right? 1 and 2. But 1 is obtained by I in here, which is already given, right? So all what we need is to prove this 2 here, and this is actually obtained by part 2 from here. So let me say 1 gives that A minus B belongs to I for all A, B in the ideal I, and we have 2, and it gives that now 2 says the product of any element from the ideal I and any other element R. So if we choose the other element R also from the ideal I, then that will mean any 2 elements of the ideal I of I, multiply them, we stay there. So that means it gives that A times B belongs to I for all A and B belongs to I. Okay, because again bar 2 says multiply any element of I with any other element from the ring. That other element from the ring could be also in I, so the multiplication stays in I as given by the hypothesis, and then we achieve the second axiom needed for a subring. Okay, so we proved I is a subring and the absorption property, so I is an ideal. Now again, before I move, if you are given a subset which is not empty and you are asked to prove this subset is a ring, then all what you need, prove only these 2 axioms. Okay, and assuming the set you have in hand is not empty. Okay, so far proving an ideal, we will use these 2 axioms with non-empty condition. Okay, now a special kind of ideal, a very simple but important one, which is called principal ideal generated by C. What does that mean? Okay, let R be a commutative ring with identity. In order to define such kind of ideals, we want to assume that we are in a commutative ring with identity, okay? And choose C. C is any element from R. And define I to be the set of all multiples of C in R. All multiples of C in R, which means I will multiply C with any other element from R. That means all multiples. That is, here we go. I equals R times C, where R is any element. Then I is an ideal. And this is denoted this way. I would like to write it here. We will use this parentheses. Actually, I like to use the parentheses with an angle. C. So if we use this, or we use a big parentheses like that, that means the set that we obtain as what? All elements from the ring, take them, all of them, and multiply each one of them by C. and then we get the set of multiples of C. Now we are saying this is an ideal, okay, and it is called the principal ideal generated by C. Okay, now to prove it is an ideal indeed, we need to show it is not empty. Sure, it is not empty because I is not empty. Why? Since 1 times C shall belong to the set, because one exists, because we said that this ring has an identity, so this is the identity of R, so it is not empty. We want to prove the other two axioms. We have already seen the theorem. Let A B belongs to I, then we want to show that A times A minus B is in I. What makes A and B in I? Then A equals R1 times C, because every element in that set, now we are denoting this by I, every element in there is a multiple of C. So A is a multiple of C and B is a multiple of C, and if we subtract now A minus B, it is simply R1 minus R2 times C, and this is a multiple of C. So it belongs to there, and this is I. Now, again, let R be any element in the ring. Then what will happen? We want to show that R times A belongs to I, but R times A is R1, R times R1C, which is A. Now use associativity. This is R1, because associativity axiom holds in the ring. Now this is a multiple of C. It is an element from the ring, which is R1 times C. So this belongs to the ideal generated by C, principal ideal generated by C, which is I. And similarly, if we multiply this way, we get A, which is A is R1 times C times R, and this equals C times R1, because we are assuming ourselves in a commutative ring. So we use commutative ring and identity to accomplish the proof, and this times R. Now use associativity, and this is an element which is a multiple of C. Multiply C by that element, so it is in the ideal, principal ideal. It is in the principal ideal generated by C, which is I. Therefore, now we have such a definition, such a thing to be ideal, and it is called principal ideal generated by C. And this simple ideal is important actually in algebra, and very important. Okay. Now, what principal ideals we might have? Let me, before I move to an example below there, which shows which gives an ideal which is not principal. So let me give a principal ideal. Simply, if we choose, so this is an example, choose the ring R to be Z. This is commutative of the identity, and choose C to be 5. So the ideal generated by C, which is ideal generated by 5, but this is all multiples of Z. Z is an integer times 5. Can I write it in this way, where Z is an integer? So I use this notation, but you know this simply. I could write 5 times Z. This simply all multiples of 5. But you know that all multiples of 5 are given this way, and we know this is a subring. Now it is an ideal, and it is generated by 5. So this is a principal ideal generated by 5. And you can do the same thing for any integer instead of 5. Now in this example, we will see an ideal which is not a principal ideal. Okay, not a principal ideal. So what is it? we have seen I, the set I of all polynomials with even constant term is an ideal. Yes, indeed. So all polynomials with integer coefficients from there, all polynomials with integer coefficients that have even constant term, they are ideal. They make ideal. But it is not principal ideal. So we will show now this is not a principal ideal. How we show it by contradiction. We will say, oh, okay, assume it is a principal ideal, so that means it is generated by some element, right? So assume the contrary. That means assume I is generated by some element. What element? From the ring. This is the ring, right? It is z of x. So the form of elements there are polynomials with constant with integer coefficient. So when we say an element from the ring, then it is a polynomial. So we write it that way, and this is for some p of x polynomial inside z of x. Okay? Okay. So we assumed that ideal, remember, it is all the set of all polynomials whose constant term is even, right? Now notice that 2 belongs to I, because it is a polynomial, it is a constant polynomial, p of x equals 2. Yes, the constant is considered as a polynomial. So 2 must belong to I. And that means 2 must be, or let me write it this way, must belong to the principal ideal generated by I. And that means p of x, so let me write it here. So p of x is a divisor of 2, but I would like to say it the following way. I will say 2 is a multiple of p of x. So 2 is a multiple of p of x, right? Because this set, the ideal generated by an element p of x, we said it is all the multiples of that element, the generator inside. Okay? Now 2 is a multiple of p of x. So what could p of x be? So that means, what are the elements that has 2 as multiples? They are only p of x equals plus negative 1, or p of x equals plus negative 2. Okay, because 2 is a multiple of these things only. Now, if p of x equals 1 or negative plus 1, then that means this ideal will equal the whole ring. So, and I will say why in green. I'm saying if p of x is 1, then that ideal contains the whole ring. Why? Because we are saying it is an ideal, and we have 1 belongs to p of x. Yes, because it is multiple of itself. That means r times 1 shall belongs to there, because it is an ideal. And this is for every r in the ring. But r times 1 is r. So that means R belongs to this ideal for every R belongs to the ring. So what we got? We got here. So how come this ideal is contained in the ring? And now we are saying that the whole ring is contained in the ideal, because I'm saying here every element R from this ring belongs to the ideal. So that means this ideal in such a case gives the whole ring, and this is wrong, right? But this cannot happen. Why? Because 3 is a constant polynomial, right? Or if you wish, say x plus 3. This is a polynomial, right? But its constant term is odd, so it does not belong to the ideal I. So this belongs, belongs to the ring, and it does not belong to the ideal I. So we got a contradiction. Contradiction to what? A contradiction to this conclusion here. So we have this conclusion here, and we have this, so we get a contradiction. What caused that contradiction? This assumption. So we cannot allow P of x to equals 1, and similarly negative 1, and therefore we are forced to take the second option. Now, so we must assume that P of x equals 2, negative or plus 2. Okay, so we will take this assumption, and this assumption will lead us to another contradiction, and then the whole step at the beginning, assuming I is the principal, was wrong. Okay, now if P of x equals 2, let's see what happened. If P of x equals 2, let's see what happened. Note here x, which is x plus 0, right? Which is equal to x, must belong to I, because the constant term is 0, is even. And we said I is the set of all polynomials that have even constant term. So x belongs to I. Now, that means x must belong to the ideal generated by P of x, which as we assumed, and therefore, but P of x is assumed, it's forced now to be 2. That means x belongs to ideal generated by 2. How this could be possible? Let's see. But okay, ideal generated by 2 means all multiples of 2, and the multiples are from z of x, right? Okay, let me rewrite this and another color in here. This part means, this is what I just said, multiples of 2. So it is g of x times 2, where g of x are elements coming from the ring, all elements coming from the ring. Okay, so this means x equals g of x times 2 for some g of x in there. How could this be possible? The only way is to have g of x to be linear, okay? Because if the power of x inside g of x is greater than 1, this equality cannot happen. So g of x must be of this form, ax plus b, where a and b are coming from z, because we are in polynomials with integer coefficients. But in such a case, we will have x equals 2ax plus 2b, and that means make equality of terms, coefficients of x. That means 1 equals 2a, and that means a equals 1 over half. And this is a contradiction. Contradiction to what? This is a contradiction to what? Because we assumed a and b are from z. Look in here, let me emphasize it. G of x are coming from the ring of polynomials with integer coefficient. So when we said for some g of x, then we are forced to choose the coefficient of that g of x to be integers. Okay, then we are forced to do so. And now keep going. We found that we are forced also to choose a to be 1/2. And this is a contradiction. So we cannot assume this. But what forced us to assume that b of x equals 2? Actually, the assumption here was wrong. So we cannot assume that. And therefore, the ideal I is not principal. And therefore, in the polynomial ring z of x, in this ring here, the set of all polynomials whose constant term is even, this set, this ideal, cannot be generated by one element. It must be actually generated by two elements, which we call, it is generated by 2 and x, and it cannot be generated by one element. And we will see this in a while. An ideal generated by two elements. Okay, some ideals are generated by more than one element. We have seen that the ones that are generated by an element are called principal ideals. Now again, let's have this theorem says assume we have a commutative ring with identity, and assume we have some collection, finite collection of elements from the ring R. Then the set I given by summation of multiples of these C's. So I equals R1C1, where R1 can be an element from the ring, R2C2, all the way, Rn-Cn, then add them all, and there is this element from the ring, is an ideal. This ideal is called finitely generated, and we denoted it this way. I may use parentheses this way. So ideal generated by C1, C2, and Cn. And the proof is exercise. Just use the two axioms. A minus b belongs to I for every a and b in I. If a is in I in this ideal, then a has the form R1C1 plus R2C2 all the way, and B has the form, say, S1C1 plus S2C2 all the way, and then subtract them, and simply the form of the subtraction will be an element of that kind, summation of multiples of the C's. And go ahead and go also prove the absorption property from the left and from the right. So this is left as an exercise for you. This is what I just said in here. In the ring, the ideal that consists of all polynomials with constant term. Let me write it here. So the ideal that consists of an x to power n all the way till we reach a1x plus a0, such that n can be any natural number, including the 0. And AI, all of them are from Z, the coefficient from Z. But now here we make the stipulation that A0 is even. So actually this is the set we have talked about in two examples already. the set of all polynomials whose coefficients are integers and the constant term is even, we can write it this way. And now we claim that I is generated by 2 and by x. And I believe I will leave that for you. Actually, I will give a sketch for that. Any element, if f of x belongs to, if we take any element in I, then it has that form, right? With ai even. So a naught, sorry. So I can write a naught as 2 times some integer, say b, where b belongs to z, right? Okay, so I can write f of x now. And before I keep going, this will be another polynomial, okay? And take x as a factor of it. So we will write an x to power as a common factor, I mean, all the way till we reach a 1, and then this is x. Now, if we add both this and that, we get f of x back. And now if we call this part here, take this part and call it, for example, h of x, right? The coefficients are integers, so the coefficients are from here. So simply we could write f of x. I said I will leave it to you, but I have already done it. So h of x is f of x is h of x times x, right, plus 2 times b. So what happened here, an arbitrary element in I could be written as a multiple of x and a multiple of 2, right? But it is in here, summation of multiples of, we can take now c1 as x and c1 as x and c2 as 2, then that will be generated by c1 c2, right? Oops, c2, which means it is generated by x and 2. So an arbitrary element in there. So let me make it clear. I want to show that I is generated by x and 2. How I do that? I pick an arbitrary element in I and rewrite it as a multiple of x plus a multiple of 2, then we are done. And that's what we wanted to do. Good. Now we go to congruences, modulo ideal, a very important thing. And this is not new to you because we have already worked with congruences modulo a normal subgroup. Okay? Now, a ring is an abelian group. So any subgroup there is normal, right? And an ideal is a subgroup, because we said an ideal is a subring and absorption property. So it is a subgroup, and we are in an abelian group. So an ideal is normal subgroup. So we can consider I, an ideal, as an extension of normal subgroups. We have already worked, when we learned about normal subgroups, we worked with congruences, right? With equivalence classes, modulo that normal subgroup. But I am saying here, an ideal is the normal subgroup, then we can do the same thing. But now we will have multiplication and addition. Actually, we worked, let me remind you, when we worked with normal subgroup, we worked with cossets, right? And then we defined an operation for the cossets. Now, I'm saying I is a normal subgroup, so we will define cossets of I. And we will define addition and multiplication of cossets of I. And that will take us to what is so-called quotient ring. We learned about quotient group, but a ring is a group. Then we will learn about quotient ring. The quotient ring is essentially a quotient group with some operation. Add one more operation that makes it as a ring. So let's go for it. To be able to do all of that, we will define congruences. So we start with an ideal I. So assume I is an ideal in R. And we will say that A and B are congruent modulo I, and here it is written A is congruent to B, and I will keep writing it this way, modulo I, okay? If and only if, same thing for subgroups, their difference belongs to I. So two elements are congruent modulo normal subgroup if their difference belongs to that normal subgroup. Same thing for ideals. Two elements are congruent modulo an ideal if their difference belongs to that ideal. And now this is a relation between the elements of the ring R, because A and B can be any two elements in the ring R. So we will say that two elements in the ring R are related if they are congruent modulo I, an ideal, because we are given an ideal. This is interesting actually. Start with the ring. Given an ideal, we will say two elements in the ring are related if they are congruent modulo that ideal. Again, we will say two elements in the ring are related if their subtraction belongs to that ideal. Good? Okay. Now, same ring, start over, start again, but choose another ideal. Then a different relation on the elements in R will be defined according to this ideal this time. Okay? Good. Now, let's stick to an ideal. Assume we have a ring and fix an ideal. Stay with an ideal. Then define the relation between elements as we have already said. Then the following theorem says this relation is an equivalence relation. And because it is equivalence relation, we can define equivalence classes, and the equivalence classes will come out to be the cossets of the ideal I. Okay, so let's do it. Let I be an ideal in the ring R. Okay, here we go, I in the ring R. And then the relation of congruence modulo I, this is what I have talked about, is reflexive, symmetric, and transitive. Let's do the proofs for a quick. Reflexive, every element is related to itself. This is true because A minus A is 0, and the 0 belongs to the ideal I, right? The 0 belongs to there because it is a subring. So we got reflexive. Symmetric, if A is congruent to B, that means A minus B belongs to I, so it equals a small I for some element. Small I in the ideal capital I. Therefore, B minus A is minus I, which is the additive additive inverse of I. I is an ideal, so it is a subring, so it is a subgroup. So if you give me a small I in there, then the additive inverse also is in there. So minus I in there, that means B is congruent to A. Now, if we choose A congruent to B, that means A minus B equals I, small I. And if we choose B congruent to C modulo I, that means B minus C equals J for some J in the ideal I. Okay. Therefore, A minus C equals all the way computed, it is I minus J. But I is an ideal. So I plus J, I an ideal, and small I, small j in the ideal I. So their addition is in there. And it is equal to A minus C, and therefore A minus C are congruent modulo I. So we got now the congruence relation between elements of a ring R. Modulo some ideal is an equivalence relation, and therefore we will define equivalence classes soon. Before we go so we will take this theorem, which is a repetition actually, and the one we already seen, the theorem we have already seen. They are repetitions of theorems that we have proved when we worked with normal subgroups. Okay, now like we have seen this theorem again, but instead of an ideal I, we use a normal subgroup. It says if A and B are congruent to an ideal I, C and D are congruent, then add A and C. It is the same thing if you add B and D. This is what we have seen in group when we talked about groups. And also multiplication, multiply AC, it is the same as multiply B and D. Do you know this theorem says A and B are the same element, modulo I, congruent, but we look at them at the same. C and D are the same. So if I multiply A and C, it is the same thing if you multiply B and D. and same thing for addition. And now the proof is so quick. We want to prove this part, a minus c, b minus d, congruent to modulo I. So we will subtract them, right? So we'll say this, subtract that. So here we go, subtract them, play with them, and then we will get this. And that's what we want. And now what about multiplication? Multiplication, there is a little trick. So we will say this minus that. Here we go. Now we add something which is BC and subtract it. Subtract it and add it. And then rewrite it in this form. And then we get that. Now we have I belongs to the ideal I, right? But we have an ideal. So IC belongs to I because of the absorption property. J belongs to I, so because of the absorption property. Bj belongs to I. Now, I is an ideal, so it is a subring. So it is a subgroup. So addition of any two elements in there, so Bj, shall stay in I, and this is what we get in here. It belongs to I. What we got, AC minus BD belongs to I, which means they are congruent. Modulo I, and then we are done. So the proof is so quick. And now we reach what I have talked about. We have congruence classes. We will not speak about classes, equivalence classes, unless we are in an equivalence relation. And we have proved that congruence modulo ideal is equivalence relation. We just proved it in the above theorem. Now, this is what we are defining here. If we start an ideal I in a ring R, and now see in here, choose an element. We want to choose an element. Stick an element in R, in R, any element. It can be from the ideal itself or outside the ideal. We want to do the following. So it's better, as I always see in algebra, it helps you to always draw figures. Say this is an ideal, okay, an ideal I, and this is an ideal I, and then we choose any element in the ring. You know what we will do now? We will say, okay, all elements in the ring, I will represent them by green. All elements in the ring, and because I chose A from outside I, then all other elements actually will be outside A for some reason. All elements in the ring that are equivalent to A modulo I, please come here. We have already said if we have a ring and then we define a relation between two elements in the ring to be related if they are congruent modulo I, if their difference belongs to I, right? Now I have a ring. I started with a specific element. And then I said, please, all elements in the ring that are congruent to A modulo I, please come here. I want to collect them in one set. Okay, so let's do it. So this is what I'm saying now. Please call all elements. So each one of these green is called B. Anyone is called B. Collect all elements B in R such that B is congruent to A modulo R. But that means B minus A belongs congruent to A modulo I mean. That means B minus A belongs to I. Oh, okay. But that means B minus A equals a small I for some small I in the ideal. Okay. And that means B equals A plus I for that small I. But small I can be any element in the ideal. Can be any element. So we got A plus I with I, any element in the ideal. So interesting. So what we got is the following. Very interesting. If you wish, we used to call this equivalence class of A. What I said, we have a ring and an ideal, and we picked an element A, and then we called for all elements that are congruent to A modulo I, and they came out to follow one form. the set in there can be described by a plus I, the ideal I itself. So what I marked in green in here, each one of these elements is a plus some small I. So the equivalence class of a is a plus I. Oh, this is so interesting. So this is the left cassette of I in R. And we have seen it before. The left cassette. Very interesting. Okay. And then we will use a left cassette to make quotient rings. Same thing when we use left cassette for normal subgroups, we started with normal subgroup, made left cassettes, and then we formed quotient groups. And we will do the same thing now with left cassettes of ideals. And what will happen here, we will write R over I to be the set of all left cassettes of I in R. Very interesting. And we have motivation to do so, right? So R over I consists of R plus I, where R is a ring in R, the ring capital R. Okay. Now, as I say, I explain too much details. I find myself. So please allow me here to help you to visualize or have some sense for what is written in here. So let's play with it. Assume we have a ring R. Okay. I will denote the ideal I. I can do that with this. I will assume this area is the ideal I. Okay. Now choose an element A. Some A. As we have done before. From outside I. And call all the elements in R that are congruent to A. But we have already seen it is A plus I. So I will say, oh, okay, this is A plus I. So I started with an element and took the left cassette of that element. Okay? Now, inside the ring R, there were a lot of elements, maybe infinitely. This is I. And a lot of elements. This is A plus I. And you know, when these are group and cassette of groups, that I and A plus I have the same number of elements. Okay. Now what's happened? Do we have elements in the ring R left? After that, elements that are not in I and not in A plus I? Yes, we have maybe some element. Maybe we have some element B, which is not in the above two sets. Then call all the elements in the rings that are congruent to B. What you are doing here, you are making a cassette of B. And we keep going. And again, choose another element C, which is does not belong to any of the above cassettes there. Take all elements in the ring that are congruent to C. That means the cassette of C. And keep going. And you will find actually the ring is partitioned as a union of disjoint cassettes. Right? And this is what I mean here. Good? Okay, good. Now, if you look at the theorem below, it says that if two elements are congruent modulo and ideal, then these two elements will give you the same cassette. For instance, what I mean in here, if I have another element, I call it, let me go back and change this to D. Why? Because I want my notation to match the theorem. If I have C in here in the same cassette as A, then the cassette of C and the cassette of A are the same. This is what we are saying. If A and C are congruent modulo I, then they give you the same cassette. Okay? And this is very important. Now, some people will say that, oh, okay, maybe the ring has infinitely many elements, so we will have infinite cassette. Then we say no, because there are infinitely many elements that are congruent to each other, and all of them, each one of them will give you the same cassette over and over and over. And you remember that when we worked with Z over 5Z, right? A lot of elements give us the same cassette. So that was R plus 5 of Z, but it was suffices enough to take R to be 0, 1, 2, 3, 4, and then we are done. So we have 5 cassettes only. So 2 congruent elements will give you the same cassette. This is proved in the following theorem, which is left an exercise, but I will do it for quick. If we prove that we want to prove it, this means here, so I will just try so quick, this means A minus C equals I for some element belongs to I, okay? And that means, so I want to prove that, right? And that means A equals C plus I, okay? So that means A belongs to, okay. So we can write it in different ways. Let me choose this to be J, this to be J, and that means A plus I equals C plus J plus I, where I is any element from the ideal I, okay? But this also belongs to I, so this belongs to C plus I. So what I have proved here, that A plus any small I belongs to C plus I. Good. Now, since A is congruent to C mod I, then C is congruent to A mod I, then the opposite thing will happen. The opposite thing of this will happen. So I'm sketching the proof here. Now, what's about the opposite? If I have A plus I equals C plus I want to show that A minus C belongs to I, right? But I have 0 belongs to this ideal, right? So I can say A plus 0, which is an element in here, but this is the same as the set. That means this belongs to C plus I, and that means A plus 0 is A equals C plus I for some small I, and that means A minus C equals that I which belongs to I, and that means A and C are congruent modulo I. So this is the sketch of the proof, but I want you to remember that 2 elements will give you the same cassette if and only if they are congruent modulo the ideal. Okay, and now actually this theorem I have just a sketch proof for theorem 6.2 and theorem 6.7. We have proved a similar thing. We have proved them already when we worked with normal subgroups, right? So I am repeating the proof here, and this is again, it says 2 cassettes of I are either disjoint, or they are identical. So to make a quick sketch for that, let's see A plus I does not equal C plus I. So they are not identical, we are saying. Then we want to prove they are disjoint. We want to show they are disjoint. Assume at the contrary they are not disjoint. Assume A plus I intersect C plus I. Will have some common common element. Say it is X belongs to this intersection. So that means x equals a plus I, and x equals c plus j for some ij in the ideal. And that means these two elements are equal. This is c plus j, but that means a minus c equals g minus I, but that belongs to I. Oh, and that means a minus c belongs to I. That means AC are congruent modulo I. So what we got, if they are not disjoint, then they are congruent modulo I, and then by the above theorem, a plus I equals c plus I. So okay, interesting. So what we have proved, if they are not disjoint, the intersection is not phi, then we concluded they are the same. So either they are not the same or they are disjoint. Okay. Now, in here, it's just what I wrote above there, R over I, again, the set of all cosets of R inside the ring R. So, I as an ideal, the set of all cosets, congruence classes. Okay. And here is an example. Z over the ideal generated by 3 consists of all cosets of the ideal generated by 3, with R is an integer, but we know this is only 0 plus this ideal, 1 the coset represented by 1, and also the coset represented by 3, right? Because simply 3, the ideal generated by 3 is 3z. So these are all the cosets in there. And now the last example is to see the cosets of the ideal I that we worked many times with it. I be the ideal consisting of all polynomials with even constant term. Again, with even constant term, we want to know what are the cosets of that element. What are the cosets of that element? So every polynomial with even constant term is in I. Now, so to make coset, you saw that we have I. Then what I did, I chose an element from outside I and then computed the coset. Correct? How I compute the coset of that element from outside I will see all elements that are congruent to it. So choose f of x, which is not in I. Okay, that means the constant term is odd. Then the constant term of f of x is odd. Okay? Now, this applies for any element. I shall say it does not belong. This applies for any element that is not in I. Good? So, if again h of x is not in I, then the same thing happen. Then the constant term of h of x is odd. Correct? Consider now, subtract f of x minus g of x. So when you subtract polynomial, you subtract the terms that has the same power of x. Now, the constant term in that subtraction will be odd minus odd, which is even. So f of x minus g of x has an even constant term. Has an even constant term, right? So that means, so f of x minus g of x belongs to I. So what happened here? We chose a specific f of x from outside I and take any other polynomial from outside I. And then we found that it is congruent to f of x modulo I. So that means, so what we concluded here, that f of x is congruent to g of x modulo I for all f of x and h of x not in I. So all polynomials that are not in the ideal I belong to the same coset. Okay? Belongs to the same coset. And we want to represent that coset. So, see again, we have I. I has all polynomials of even constant term. So if you take one of them plus I, then that will describe that coset, right? Again, because we have a coset, a lot of element, infinitely many element. How we represent it? How we represent it? The above theorem says, look in here, this is how algebra is understood. The above theorem in here, it says it does not matter how you present it. So look at this theorem, very interesting, very interesting. It says, okay, if you have two elements that are congruent modulo I, then you can use any of them to represent the coset. So if you have a coset that has infinitely many elements in there, which one you choose to represent the coset? Answer is anyone, any element, because all of them will give you always the same coset. Got it? Okay. So let's go back to the ideal below there. So the ideal itself consists, the coset of the ideal itself, which is I, consists of all polynomials whose constant term is even. So give me a polynomial of that kind and make a coset of it, and give me the simplest one, which is 0. So now we will use 0 plus I to denote I. This is the first coset. Go to the other coset. We said all other polynomials from outside I have odd constant term, and every two of them are congruent modulo I. So the other coset will contain all polynomials whose constant term is odd. Give me one of them to represent the coset, the simplest one. What do you think? Why don't we choose 1? 1 is a polynomial of constant term, plus I. Now we said we have two cosets only, and that simply is the factoring that we will call over the ideal I. Ideal I, what is the ideal I? Which is generated by 2 and x. Very interesting. Two cosets of that ideal in that ring. Great. And this brings us to the end. I believe we have nothing left to work. Okay, we are done. Thank you.